to another video on axiomatic thermodynamics, and today we'll be getting to know about the first law of thermodynamics. And there was one more of it. Right, the first law, which is basically conservation of energy in thermodynamics. Conservation of energy. That was introduced in thermodynamics for obvious reasons, and the fact that it actually goes much more than just conservation will be explored later on in the video. Right, so the first law, as I said before, energy is conserved. Yay. But what are these different variables that we are right now seeing on the screen? Like, in thermodynamics, you have different kinds of energy and work done, which is basically synonymous, but different kinds of energy, whereby E is the inner energy or the internal energy of a system, Q is the heat or heat energy, and W is the work. Right, and how do you define them? Inner energy, the definition of inner energy is understood in various ways in many books, but by how I understand it, it is the part of energy of a system which is not really that much dependent on the very, very minute which is not really dependent on the macroscopic degrees of freedom. So, like, let's say the movement of let's say if we have a system and we have a center point and it moves, then this is not really the part of the inner energy. The inner energy is basically the sum of all the minute kinetic and potential energies of every such particle which is inside the system. So every such microscopic system. The definition in itself is, again, not very it doesn't give you much perspective until you actually move into statistical physics. Then the picture becomes much clearer, but as of now, yes, it's the sum of all microscopic kinetic and potential energies. One could see it as that. Work is then somehow the energy that is needed to change macroscopic degrees of freedom. So let's say we can say that work could be like defined as like the change of work, of course, it's as pressure times the change of volume, or along with that you can also take the magnetic field times the dipole moment, and then you also have, let's say, the summation of all the chemical potentials time the change of the amount of particles that's inside. And there are many such terms which basically signify how much work is how much energy is put inside the system to change the macroscopic degrees of freedom. This formula, obviously, it goes for a quasi-static process. And the funny thing that you see here is also firstly a Q. What is this Q? It is, as you see here, heat. It doesn't really have that much of a strong definition. I would say that Q is basically the amount of inner energy that does not go into changing the macroscopic degrees of freedom. And yeah, that's about it. But what really is the difference between such a D and such a change, such a delta, which is also a Greek alphabet for D, the difference can be seen as follows in my eyes, which is basically if you have a system at time t0 where, let's say, you are measuring energy and the energy is E1, And then you have another system whereby the t is equal to 2 seconds, let's say, and the energy changes to E2. So you can physically see the change of the system's state. It is a measurable observable which changes over time, and you can see both the ends. Right, you can also probably see it from, let's say, a small volume to a bigger volume. If it changes, you can also see the difference. However, for heat and work, those are not really any state variables, because you do not really see the change of state of the system, but those are very, very minuscule amounts of energy that are put inside the system to change something or the other. So you really put like some form of work in order to compress this system, then the change of volume is very much understandable, it is seen, but the change of work does not really mean much, because the work was given from the surroundings into the system, and you do not really see its two endpoints. So it is not really a state variable. It is something that you put inside the system for its state variables to be changed. Right. And one exactly is the total differential or the absolute differential equaling a partial of it. It is only possible when they can be changed, like the order can be changed of the partial differentiation. But again, this is not a maths video, but we'll for sure be going into the core of this mathematical concept in another video, which I'll probably put a link in the description too. And yes, but that's all about it for the first law of thermodynamics. This can be used obviously in defining different cyclic processes, like the Carnot cyclic process or the Stirling cyclic process. There are various forms of definitions that come out of such processes, which were mainly defined in the time of industrial era to work with different kinds of machines. And the cyclic processes are then very important in axiomatic thermodynamics, because again, they serve the objective of describing different kinds of machines, thermal machines, and different kind of work done by the machines. And we'll see how the efficiency of such a process is then defined. Right, but all of them can be done through while using the first law of thermodynamics, which is really our second axiom. And then we have 2 more to go. So thank you again for watching this video. I hope it could clear some doubts of yours and clear some of the concepts. If you like the video, of course, press a like and share with your friends, and let me know in the comments if you would like anything changed in the next videos. Thank you.